Hi everyone, welcome to our electrochemistry video. This is the final unit of Chem 1 AO3, and I just want to say congrats to everyone for making it this far, and let's get started. What is the oxidation number of manganese and MnO4- and an Mn2O3 respectively? So I'm gonna write it bigger, and the key with these questions is just knowing a couple ground rules. So number one, oxygen is usually always -2 oxidation number. And then another important rule is that all of the oxidation numbers from each of the elements in the species have to add up and equal the overall charge of the species. So what I mean by this is you'll see in the first one, so oxygen is -2 and we have 4 oxygen, so I'm going to multiply that by 2. And this will give me -8. And then I want to find out what the oxidation number of manganese is, but the overall charge of this species is -1. So I know whatever it is, it has to, when it's subtracted by 8, it has to equal -1, and this will give me +7. So that's oxidation number of the first one. And then the second one, I have 3 oxygens, so -6, and then the overall charge of the species is 0. So I know that the Mn2 has to be +6. And then because we had 2 manganese, which was 6, then I know that for 1 manganese it has to be +3. So therefore, my oxidation numbers are +7 and +3. Okay, question 2, identify the oxidizing agent in the following unbalanced redox reaction. So the oxidizing agent is the one that is reduced. So I'll just say it is reduced. And then the other way around, if it's a reducing agent, that means it itself is oxidized. So for this question, I'm just going to write it bigger on this side. And then basically we just do the same thing. We have to figure out first the individual oxidation numbers, and then we can see, did it lose, did it gain electrons. So for the first one, I have oxygen, so -2, and I have 7, so this multiply by 7, and you get -14, and it has to add up to -2, and we know that Cr2 is +12. So then for 1 Cr, it will be +6. And then we have Fe2 plus. So for individuals, like elements, like this one, the oxidation number is just equal to the charge. So it's +2. And then for Cr3 plus, this is +3, and then also +3. And then I'm kind of ignoring H plus and H2O because hydrogen and oxygen, they kind of have constant oxidation numbers. So what we want to focus on is the ones with like chromium and iron. So we found the oxidation numbers. Now we need to figure out which one's reduced, which one's oxidized. You can use this trick oil rig, which stands for oxidation is loss of electrons and reduction is gain of electrons. There's also another one that's like Leo the line goes gur, but I think this one's a bit easier to remember. So oxidation is loss of electrons. So loss of electrons will mean that it's getting more negative or less positive. So Cr went from +6 to +3. This is gain of electrons because it's getting more negative or less positive. So I can say that Cr is going to be the one that's reduced. And then for iron, it's going from +2 to +3. This is losing electrons because it's getting more positive. So I can say that iron was oxidized. And then the oxidizing agent is the one that was reduced, which is the one with chromium. And with these like agent things, it's always going to be the whole entire species and not just the element. So therefore, the species that is being reduced is Cr2O7 2 minus. Okay, question 3, very important question. Balance the following redox reaction under acidic solution conditions using the smallest possible integer coefficients. So, very important to know how to balance equations. So let's go through this step by step because it's a lot more complicated than your regular balancing. Okay, I'm going to write out the steps in black as well. So first step is you want to write the half reactions out. And you also want to balance the non-oxygen or hydrogen species. So what I mean is you're going to split up this equation that you see into half reactions. So one half reaction will be Cr2O7 2 minus, and then Cr3 plus, and then the other half will be Fe2 plus to Fe3 plus. And then with these, we have to balance the non-oxygen or hydrogen species. So what I mean is that we have Cr2 here, but only one Cr here, so I have to add a coefficient of 2 in front. And then although we have 7 oxygens here, we don't care about the oxygens or hydrogens as of right now. And then let's figure out what the oxidation numbers are. This one is +3. This one, -2 times 7, -14. Okay, so Cr is +6. And then here, obviously, it's just +2 and +3. So basically, we have one oxidation reaction and one reduction reaction. That's how we split it up. Okay, step 1 is done. Step 2 is we want to add electrons anywhere we need in order to balance the charges. So for my reduction reaction in blue, we're going to add 6 electrons because we have a oxidation number difference of 3 between the two CRs, but then we have 2 CRs, so we have to multiply that by 2. So we add 6 electrons. And then that's how we balance the charge. And then for Fe2 plus and Fe3 plus, we had +2 and +3. So what we have to do is add an electron here to balance the charge. Okay, step 2 is done. Step 3 is to balance the remaining species, which are just oxygen and hydrogen, using H plus and H2O. So for our reduction reaction, let's balance this. So a trick is to add whatever H2O you need first and then add the H plus to balance it after, because we only have one oxygen And then we can just add however many H2Os we need in order to balance the oxygen. But then after we add this, the number of hydrogens is going to change. So it's going to be much easier to do that first and then just add the necessary hydrogen that we need afterwards. So in this case, I have 7 oxygen, so I have to add 7 waters to it. And then after that, I can add hydrogen, which I have 14. So on the other side, I'm going to add 14 H pluses. And then for the other side, you would do the same, but in this case, we don't have to balance anything else because we don't have any oxygen or hydrogen in here. Okay. Next, step 4 is multiply the equations to cancel out the electrons. So this is kind of like a system of equations in math. Basically, you just want to like play around and multiply the equations so that there is an equal number of electrons in both reactions so that we can cancel it out. So I see that I have 6 over here and only 1 over here, so that means I need to multiply the oxidation reaction by 6, which will give me 6Fe2 plus 6Fe3 plus 6 electrons. And this allows me to do step 5, which is add the 2 equations together and cancel out any species that occur in opposite sides in both the reactions. So I can cancel out the 6 electrons because they're common in both and on opposite sides. And that's all I can cancel out for now. So I'm going to write out the new equation when we have added everything together. And then because it's in an acid condition, I can keep the H pluses that are in here, and then this will be my final equation. So what was the question even asking? What is the coefficient in front of H plus in the fully balanced equation? That is 14. Hi, this is me editing. I forgot to mention that I have a whole separate video on this called Balancing Redox Reactions. So if you want more practice, you can go look at that. Look for the link in the description. So that's how you balance an equation. Now, what if it's in a basic solution? Well, it's actually the same thing, except we just have to add an extra step or two at the very end. So let's repeat what we did in the last question. So you write out the half reactions, split it up into the oxidation and reduction half reaction. So I'll have the manganese one on one side and then the iodine one on the other side. Let's figure out what the oxidation numbers are. So the oxygens make -8, and these have to make -1, so this is +7. And then on this side, it's +4. And then over here, remember that if you have just like one species, then it's equal to the charge of it, which is -1. And then this one doesn't have a charge, so it's just 0. And then we also need to balance the non-O or H reactions, which I just did by adding a 2 in front of the I minus. Okay, next we add as many electrons as we need in order to balance the charge. So because oxidation number was -1 here and -4 here, I need to add 3 electrons to this side. And then on this side, I have -1 here, but 0 on the other side. So I need to add an electron, but I add 2 electrons because of the coefficient of 2 here. So next step, after the charges have balanced, then we balance H and O by adding H2O and then H plus after. So how do we balance the oxygen first? The right side is short 2 oxygen, so I'll add 2 H2Os. And then now I'll focus on balancing the hydrogens, which I have 4 on this side and none on this side. So I'll add 4 H pluses to the reactant side. And then for our red reaction, we don't have any O's or H's, so we don't have to worry about that step. And then the next step is to multiply the equations to cancel out the electrons. So I have 3 electrons here, 2 electrons here. So that means if I multiply this by 2 and multiply this by 3, we'll get 6 in both equations, and then we can cancel those out. So let's multiply it. I'll have 8 H pluses now, 2 MnO4 minus, 6 electrons, 2 MnO2, and then 4 waters. And then on this side, I'll have 6 I minuses, and then I'll have 3 I2s, 6 electrons, and now I can cancel it out. And then just like last time, once we get to this step, we add up the 2 equations. And that would be the end if we were working in a acidic solution, but this is basic. So this means this H plus we see over here, we can't have that because it's basic. So we need to get rid of it, and you do that by adding OH minuses in order to cancel it out. So if I have 8 H pluses, then I need to add 8 OH minuses. And then when these two combine, it will make 8 waters. Because an OH minus and an H plus make water. So 8 waters. And then I'll write out the rest. And then whatever I do to the reactant side, I have to do to the product side. So I have to add the 8 OHs to this side as well. And then the final step, if you can, remember that if we have any of the same species on both sides, we can cancel it out because we want the simplest coefficients that we have. So I see that I have 8 waters here and I have 4 waters on this side, so I can get rid of it here, and then there will be 4 waters left. And then we can finally write out the final equation. And because it's basic, we can have this OH minus. So the question was asking what's the coefficient in front of H2O? It is 4. Okay, question 5. What is the correct cell diagram for the following spontaneous reaction at standard conditions? So I think cell diagrams are pretty straightforward. You just have to know some basic rules. So basically in a cell, in a voltaic cell system, at the anode there's oxidation, and then reduction happens at the cathode. So another thing is that the anode or the oxidation is written on the left hand side of these two straight lines that you see in the middle, and then the cathode or the reduction side has to be written on the right side. So all we have to do is figure out between nickel and tin which one is oxidized and which one is reduced. So I'll write the equation over here. And then let's figure out what the oxidation numbers are. So solid nickel is going to be 0, +2, +2, 0. So nickel went from 0 to +2, which means it lost electrons. So this is going to be oxidized, and it's the anode. And then tin went from +2 to 0, meaning it gained electrons, meaning it was reduced, and it's at the cathode. So now we know that nickel has to be on the left-hand side, and then we always write the electrode or the solid on the very edge, and then we have the aqueous form in the middle, and then we do 2 bars to separate the oxidation and reduction, and then same thing, the aqueous part is on the inside, and then on the outer side you have the solid electrode. So this is what the final cell diagram will look like, which is option A. And then like these options like C, you can just completely get rid of it because we don't have these like double bars everywhere. Okay, question 6. From the standard reduction potentials below, identify the best oxidizing agent. So some things to note. The best oxidizing agent is equivalent to saying it's the most easily reduced. And because this E naught it stands for reduction potential, so a higher E naught means higher potential of reduction, which is more easily reduced. So basically all we're looking for is the most positive reduction potential value, which is 1.51, which should be MnO4 or minus. Okay, question 7. Using the standard reduction potentials below, write the spontaneous cell reaction and calculate its E cell. So what we have to do is write the redox equation. So remember that the higher reduction potential is the one that's going to proceed forward, and that's the one with iron. So I'll write this as it is right now. And then the one with the lower E naught has to be flipped. So this is what the two equations will look like. And then very quickly, we know that we have to multiply this by 2. And then once we do that, cancel it out and then add it all together. Our final balanced redox equation will be 2Fe3 plus SN2 plus makes 2Fe2 plus SN4 plus. So we did one part. Now we have to calculate what the E cell is. So standard reduction potential is always cathode minus anode. which will be 0.77. Remember, the cathode is always the more positive value, and then minus 0.15, and we'll get 0.62. And just as a side note, although we did multiply this equation by 2 and we flipped the other equation, we don't have to change the values of reduction potential because it is an intensive property. So it's not like when we did those Hess's law problems and we had to change a bunch of values before adding them. This is an intensive property, meaning it doesn't matter how much we have, or if you flip the equation, it's going to be the same. So that's nice. It keeps it simple. So this is option A. Okay, question 8 for the cell reaction in question 7, which is the same thing. Oh, I guess you could have looked here, find the answer. Ignore that. Calculate the Gibbs energy at 25 degrees Celsius. So this equation is the one we need to use. This was in the lecture slides, but it's actually not on your formula sheet, which is kind of weird. But my advice is just, I think this is the only thing that you really need to memorize, if I remember correctly. So all of the other equations, they're given to you, but this one, it's just really helpful if you remember. So I'll say memorize this. It's okay, it's just one equation. And then let's see what we need to find. So we know the standard reduction potential already. We know the Faraday constant, which is given to us on the formula sheet over here. So what we need to find is what Z is. And Z is the number of electrons that was transferred. And in order to do that, this is kind of, I'll go up to when we were balancing it. So the Z value is basically electrons transferred, which is the amount of electrons you had when you canceled it out. So basically, we had to like multiply this by 3, multiply this by 2, and then get 6 electrons, and then we canceled it out at 6 electrons. So that's what the Z value is going to be. So we just do the same thing here and find out how many electrons we had when we canceled it. So write out the half reactions again. And then also the oxidation numbers. So this is plus 3, this is plus 2. So I have a difference of plus 1, but I have coefficients of 2, so I have to add 2 electrons. And then for the other half, we have plus 2 and plus 4. So I'll add plus 2 electrons on this side. And then in this case, we have the same on both sides, which is 2 electrons, and then we can cancel it out at this point. So that means that here Z equals 2. But for example, like if it's not the same, if we had, for example, 3 electrons here and then 2 electrons here, we would have to multiply it so that they're the same. And then in this case, the Z would be 6. But right now we have 2. So, and then now we just plug it into the equation. So 2 times the constant times E cell, which is given to us, or we found it in the last question. And then we will get negative 120 kilojoules per mole, which is option A. Okay, next question 9. For the same cell reaction, calculate the equilibrium constant K. So this is pretty simple. We just have to use a different formula. And this one, thankfully, is on the formula sheet. So we need one with K, and it's right over here in this equation. So the equation is delta G naught equals negative RT ln K. And then because it's the same cell reaction, for delta G, let's just use the same value that we found. But remember that this one is in kilojoules per mole, but we want it to be in joules per mole. So we have to add or like multiply it by 1,000 when we're calculating it. So R is a constant. T is temperature, but in Kelvin. So remember it's 298 and then ln K. And then when you calculate this, you'll get 9.37 times 10 to the 20, which is option B. And then I guess if anyone has questions of why it had to be in joules, remember that the R value that we're using is 8.314 joules per Kelvin mole. So that's why we had to convert the kilojoules to joules. Okay, question 10. For the reaction, will increasing the concentration of SN4 plus cause E cell to increase or decrease? So this is a fun logic question. So let's use one of the formulas to logic it out. So let's use this one. So E equals E naught minus RT ZF ln Q. The reason why I chose this one is because we have E cell here, which is what we're looking for. And then we also have this Q value. And because we're talking about increasing the concentrations of one of the species, this Q value, because Q equals Fe2 plus squared times SN4 plus. This is from the equilibrium unit, and it's products over reactants. So this is what Q equals. And then we increased SN4 plus. So if this increases, because it's on the numerator, Q will increase. And if Q increases, E cell would decrease because it's being minused by Q. So that means that it's gonna decrease. Okay, question 11. In an electrochemical cell, Ag plus is reduced by Fe2 plus. They give us the concentrations of both iron species, and the observed cell potential is 0.018 volts. Calculate concentration of Ag plus at 25 degrees Celsius. So this is going to be the same question as before, or not question, the same formula as before. So they give us the two half reactions, and then we have to combine it to make the overall reaction. So remember that the cathode is going to be forward, so we don't flip it, because this value is higher than this one, and then we flip this equation. And then we can cancel out the electrons, and our overall redox equation will be this. And then when we want to calculate this concentration, they tell us what the observed cell potential is. So I know the formula has to include E cell, which is this one. So we use the Nernst equation. So E cell equals standard reduction potential minus, so this is the equation, but then because we have two constants, we have R and also F, on the formula sheet, they kind of already input those values. So we could just get rid of those and then use either one of these. Personally, I like to use natural log. So that's what I'm going to use, but you could use either one. So 0.0257 over Z ln Q. And then, so they tell us that E cell, or the observed cell potential, is 0.018. And then the standard reduction potential, remember, is cathode minus anode. Which is 0.80 minus 0.77. So it's 0.03. And then the Z value is 1. And then ln Q. And then if you solve for Q, you'll get 1.595. Remember that this is just e to the power of that, in case you forgot how to calculate it. And then finally, they're asking for concentration of Ag+. So we know that Q equals products over reactants. So Fe3 plus over Ag plus times Fe2 plus. And then we don't include the Ag because it's a solid and there's no concentration of a solid. So they tell us the two Fe values and then we just solve for Ag plus. So we know Q is 1.595. Fe3 is 0.4. And then Fe2 plus was 0.1. So if you solve for Ag plus, it's 2.5. Okay, question 12. What is E cell for the following concentration cell at 25 degrees Celsius? So this is the same equation as the one we used above. So the one that is reduced is the one on the right hand side of the equation. So right, this is the reduction half reaction and then the oxidation half reaction. Remember, oxidation occurs at the anode, so it's the one on the left. Yeah. So it's the 0.001 molar and then plus E. And then you cancel these out and then you can write out the full reaction after, which is Ag plus 0.1 molar plus solid silver, and then the dilute one is on this side. Okay, so formula again. E cell equals E naught cell minus 0.0257 Z ln Q. And then we're calculating for E cell. We know that E naught cell, because this is a concentration cell, which means it's the same element on both sides, or both of the electrodes are the same. They're both silver in this case, so that means standard reduction potential is 0 in a concentration cell. So I'll write that concentration cell E naught cell equals 0. So I'm just left with 0.0257 over 1. And then ln Q, which is product over reactant, and the product is the dilute one over the concentrated one. And then this is what you calculate, and you'll get 0.118, which is C. Okay, which of the following processes describes an electrolytic cell? So, the important thing to know, electrolytic cells are non-spontaneous. And this means that it requires an external source of power. So, looking at option A, it says proceeding spontaneously in a beaker. So, it can't be this one. And then, same with C and D, these batteries are all spontaneous because it can create power on its own. So, therefore, using an external power source, which is the definition of non spontaneous, to electroplate a thin layer of gold onto a bracelet. That's an electrolytic cell. Question 14. In the chloralkali process, concentrated NaCl is electrolyzed to produce Cl2 gas and H2 gas and NaOH. Which half reaction occurs at the anode? So, there's a very quick and simple way to answer this question, and that is that the anode oxidation occurs. What is oxidation? Oxidation is loss of electrons. And if you first just take a look at all of our options, there's only one where we see a loss of electrons, which is option B. So you can very quickly figure it out like that. Okay, question 15. The discharge reaction of a lithium ion battery is this. Given that one electron is transferred per Li plus ion, calculate delta G for this reaction at 25 degrees Celsius. So once again, we'll use this equation. And you know it because you've memorized it by now, right? And we literally just have to plug it in. So they already told us that Z is 1. We know what the constant is. And then E naught is already given to us. Super simple. And then this will be negative 405 kilojoules per mole. Okay, 16. Which combination of signs correctly describes a spontaneous redox reaction at standard conditions? So, if I remember correctly, we were given like a chart where it said all of these like different circumstances, and then like if this is positive, if this is negative, it will be spontaneous, non-spontaneous. So with this question, I'm going to show you how to do it using logic and not having to just memorize it. So we'll need two equations. This is one, which you will have memorized for the test. And this is the other one, which is the one on the formula sheet. And then with these two equations, it encompasses everything we need because we're looking for delta G, E cell, and then K. And then these all appear within the two equations. So with the spontaneous reaction, delta G naught is negative. So then if this is a negative value, that means E cell has to be positive, right? Because we have a negative sign here. This is negative. I'll do that. This is negative. We have a negative sign here, so E cell has to be positive. So this is greater than 0. And then for K, we do the same thing. This is negative, which means that because we have a negative here, ln K has to be positive, and then K has to be greater than 1 for this to happen. and that's how we figured it out. So the one that matches everything that we found is B. 17, write the correct cell diagram using an inert PT electrode for the spontaneous reaction. So basically, this is the same thing as we did before. So zinc has been oxidized, right? Because it went from 0 to +2, it lost electrons. So because it lost electrons, it's oxidized, and this is at the anode, which is on the left. And then we know that then H has to be on the right. So then remember that we write the electrode or the solid, which is a solid, on the very outside, and then inside we write the aqueous species, and then our cathode is on the right side. So we have H plus aqueous, H2 gas, and then when we have an inert electrode, we write that on the very right side with another bar separating it. So this is just honestly just notation that you have to know. Once you learn it, it's very easy. And this matches option A. Okay, last question. In an electrochemical cell, Cr2O72- is reduced by Sn2+. They give us the two half reactions and also the overall balanced reaction if all of these have these concentrations and pH is 0. Calculate each cell at 25 degrees Celsius. So whenever it asks us to calculate cell potential, we know that it's this equation that we need, the Nernst equation. And then honestly, we can just plug these values in. So remember that standard reduction potential is cathode minus anode, and cathode is the more positive one. So this is 1.33 minus 0.15, 0.0257. And then for Z, it's the electrons transferred. So we need to cancel out the electrons, and how we do it is multiplying this one by 3. So this will become 6, and then you can cancel it on both sides. So then our Z value is 6 ln. Q, remember, is products over reactants. So I have all of the products and reactants written in the overall equation that they gave us. So this will be SN4 plus, which is 0.6 to the power of 3. Remember the coefficients. I can ignore water, and then Cr3 plus is 0.5 squared. And then for the reactants, we have 0.2 times SN2 plus, which is 0.3 to the power of 3. And then for H plus, they don't directly tell us what the concentration is, but remember they gave us the pH, and we know that concentration of H plus is 10 to the power of negative pH, or just 10 to the 0, and then anything to the power of 0 is 1. So just multiply it by 1. And then this will be to the power of 14 because coefficient 14, but doesn't really matter. And then when we calculate this, you should get around 1.18 volts, which is option B. So that was the final question we have. Thanks everyone for watching. This is the final Chem 1 AO3 video. But I'm not going to leave you hanging for 1 AO3, so check out those videos too next semester. And good luck everybody on the final exam.